Okay, welcome everyone. We are really happy to have Edward around and giving us this talk. He's going to be around today and Monday.
And Monday, yeah.
And where's your office?
I forget exactly, 3:30, I think.
Somewhere there?
9:30.
Which
That way.
point to it? That way. So seek him out. You want to discuss physics?
That's good.
And today he's going to tell us about how to derive the simplest gauge gravity duality. Take it away, Edward.
Okay, well, thank you very much. So thanks all for coming. I know it's an extra seminar during the week, so I'll try to keep it entertaining. So what I want to tell you today a bit is about some work I've been doing with Rajesh Gopakumar over the last couple of years. Well, it'll be a sliver of kind of a more general program of trying to understand how one might go about to derive something like gauge string duality. And today will all be about finding the simplest example where we can sort of make that precise. And in particular, the sort of slogan you should take away from today is that we're trying to implement sort of this very old picture of Hooft, that large N gauge theories can sort of reorganize themselves into string theories. And the slogan to take away is that somehow the Feynman diagrams of the gauge theory should map onto world sheets of strings. Okay? And you know, it's always been a kind of suggestive picture. You draw some Feynman diagrams, the 1/n expansion looks like some sort of topological expansion, but how do you really turn that into a sort of real duality? Okay, so the whole game of today is going to be trying to make this precise, okay, in some very simple toy model. So, okay, maybe just so we're all on the same page, I'll try to maybe articulate a little the vision of holography I'll be taking today. You know, often when we think about holography, maybe it's helpful to think in terms of these three boxes. So on one hand, you would have your favorite large N gauge theory here. Okay, and we would think of this as sort of the boundary. Okay, this would be the CFT and AD of CFT. And often we try to think about, if you want, deciphering the hologram in some sense, of trying to translate directly to these bulk products. Okay, so in some low energy approximation, this is like GR and QFT. Today the perspective is maybe going to be a little old-fashioned in some sense, but we're actually going to be trying to think about how to go from the gauge theory directly to the closed string world sheet. Okay. So, you know, if this is ABS, CFT, this would be, say, like type 2B on ABS5 process. So we're going to be far from that, but that's sort of maybe mentally where you can kind of place things. And the derivation of the duality is going to be really focusing here, and this is really the whole idea of kind of Hooft. Okay, so we're going to ask, can we go from the Feynman diagrams of the gauge theory to the world sheets of these closed strings? Okay, so to make that a tractable problem, we're going to have to make some strong simplifications. So the simplification we're going to make today is to look at Feynman diagrams, where if you want, we set all the propagators to 1. So we're going to look at all the edges and just set the propagators to 1. Okay. So what this is basically a 0 plus 0 dimensional integral. Okay. 0 plus 0 dimensional integral, which is just a matrix integral. So the whole path integral is just a standard integral over n squared variables. So that is this simplest gauge theory that we're going to look at here. Okay. So this is sort of modding out by the volume factor of the gauge group. The one remaining matrix is sort of an n by n Hermitian matrix. And we'll start with something very simple, just the Gaussian potential, okay? Trace m squared. And all interacting pieces of this potential we'll think about in a Hooft expansion, so perturbatively around the free theory. That's what these Feynman diagrams are, right? So in fact, actually, what we'll start out today is just looking just purely at the Gaussian matrix model, GUE ensemble.
What string theory do you expect to get as a dual for this?
Good. So what we're going to get are going to be, if you want, this is the simplest gauge theory. We're going to get the simplest string theories, and they're going to turn out to be certain topological strings. That's what's going to come out.
Edward?
Yeah.
So this is 0 plus 0, and the world sheet is 1 plus 1.
Yep.
Why are the dimension 2 different instead of 1 different?
Oh.
Well, I guess that's even weird anyway, because that would be the bulk being 1 dimension.
Yeah.
Never
Yeah.
mind.
You're maybe thinking about like JT or something like that.
Yeah.
So, when I talk about 2D surfaces, I'm really talking about the world sheet of some string theory. You can reinterpret a lot of things I say in terms of some 2D spacetimes along the lines of JT gravity. Okay. But So we'll start with this. And so what are the observables of this theory? They're just going to be sort of single trace operators. Okay, so they're invariant under a global unitary transformation of this matrix. So I can probe this system by sort of plugging in some traces inside this matrix path integral.
Are you going to comment on the relation to the IKKD matrix model?
No.
Because that's where there's some mysterious 10-dimensional space-time that arise from even a 0-dimensional matrix.
Yeah, so there's no 10D target space here. So either there'll be a sort of Calabi-Yau target, or in some presentation there'll just be a 2D target. It's an A model.
But the IKKD will be a supersymmetric version of this with potential.
Yeah, so it turns out, well, maybe I'll comment on this a little. It turns out that a lot of these matrix integrals can be obtained from some sort of localization of the gauge theory. Or there's a very nice older story by Dijkgraaf and Waffe where you wrap some brains in a topological string, and the open strings, the full open string field theory, can reduce to something as simple as the Gaussian matrix model. It's a really beautiful paper from the early 2000s.
But the IKKD also arises from the incident calculation.
Agreed, yeah. So it would be great to understand how that works. Yeah. So, okay, let me try to just kind of first state the result of today. I'll try to delineate a little the results from the maybe hopes and dreams. So what is the thing we're going to do is that we're going to map every observable like this in the gauge theory. So these are going to be connected endpoint functions. And I'm going to use this label G for the genus. And what I mean by that is that you can calculate this and do a 1/n expansion. Okay. And there will be terms, there will be coefficients that multiply the factor of n to the 2 minus 2g. What I'm calling here is that particular factor, which is one number in the 1/n expansion. Okay. And this is going to be equal to, again, an endpoint function of particular vertex operators. Okay, labeled by the same numbers over here. Turns out they have a discrete label. Calculated in a closed string worldsheet of genus G. Okay, and I'm going to tell you what that worldsheet theory is. So these will have some Lagrangians, and we'll be able to even write that down. Okay, is the result maybe clear? Sort of what we want to show today.
So you're constructing one dual, but potentially there could be multiple candidate worldsheets.
So in fact, actually, we have 3 duals, and I'll talk mostly about one of them today. So I'll tell you what these worldsheet theories are. Okay, good. So let me maybe just make some comments, especially for people who don't think too much about these things. So one thing I want to emphasize here is that we're not looking at any double scaling limit. So let me try to say what that is. Okay, so matrix model and strings is a super old subject. You would think that there's probably nothing new to add, especially about the Gaussian matrix model. And sort of in the 90s, when people started first thinking about that, they already had some idea of this Hooft vision. You know, can we relate the Feynman diagrams to some sort of 2D surfaces? And the way they thought about that was that somehow the Feynman diagrams, as some sort of discretization of the worldsheet. Okay. And if you want, there was an additional limit you needed to do, which is on the matrix model side, what's called the double scaling limit. And that corresponds to sort of taking the size of the discretization of this 2D surface to 0. It's a continuum limit on the worldsheet. Okay? So what's sort of quite important today is that we're not going to be taking that limit, and this is not going to be the picture as to how these 2D surfaces arise. And the reason why this is an important point, it might seem academic, is that there's no double scaling limit in something like ADS-CFT. Okay, so also does not arise in ADS-CFT. So if you imagine that the mechanism of, say, how n equals 4 Feynman diagrams become some worldsheets of type 2B strings, it certainly can't be this picture. So a large thing I'm going to be trying to do today is to tell you how to replace this picture, okay? How precisely to go between some Feynman diagrams and some 2D surfaces. Okay. Yeah, is this point clear? Okay. Good. So let's maybe go directly to that. Okay, so before we dive into the weeds of trying to derive this result, maybe I'll try to distill kind of 2 main takeaways that we've learned from this program, and I think that are certainly much more broader than just these matrix models. So it's precisely this question then, if we're not going to think of the Feynman diagram as some sort of discretized 2D surface, how are we going to translate between Feynman diagrams of the gauge theory and a sum over 2D surfaces in the string theory? Okay. So I'll try to give you two answers. One is going to first seem a little mathematical, and then I'll try to physically say what's going on. Okay. So the mathematical statement is that we're going to use something called the Strabel parametrization so this is the moduli space of Riemann surfaces of genus G with n marked points. So these marked points are, say, where you would insert vertex operators. And then n positive numbers, okay, r plus to 3. Okay. So what is this? I'm assuming probably most people haven't seen something like this, so I'll just try to give you a rough taste of what it is. So what is it? It's an exact equivalence. Okay, so this is the important word here. Between, on one hand, what I'll say what this is. So, ribbon graphs are just sort of the Feynman diagrams and this double line notation of Hooft. Metrized is going to say that we're going to assign a particular length to every edge. Okay. They're going to be of genus G, okay, and they're going to say, let's say, n faces. And over here, this is going to be a point on MGN times R plus n. There's going to be a very precise dictionary to go from this Feynman diagram to a point on the moduli space. The point on the moduli space is one particular 2D surface up to equivalences. Okay. So let's try to draw one of these. Okay, so imagine I want to describe some 4-point function of a string. Okay, so it would be some genus 0 here. G equals to 0 here, and this will have n equals to 4, different n equals 4. Yeah. Okay, so 4 insertions. Okay, so 1, 2, 3, and 4. And this particular surface has some moduli. What are they? You know, if you do this computation, say you can fix by SL2C invariance 3 of these points, and the remaining modulus is sort of where I put the 4th point. That would be the moduli of the surface. So what are these graphs going to look like on this side? Okay. So these are going to be graphs that are built out of generically trivalent vertices. And they'll look something like this. Okay, great. So what is the genus of the surface over here? Well, here it's just defined very simply by v minus e plus f is 2 minus 2g. Okay, and in this case, you'll see that g is also equal to 0. So the genus of this graph is going to be the genus of the Riemann surface. The number of faces, so the number of faces is equal to the number of insertions here. It's going to be a sort of important point later. Okay. So in particular here, we have 1 face, 2 face, 3 face, 4 face. Okay. So what's so the lengths, I'm going to assign lengths to the edges, and these are going to map onto the moduli, or if you want, these are going to be coordinates on MGN times R plus n. So any questions just about this statement?
So the individuals, like with the R plus parameters, they are mapping to the size of the surface?
Great, great, great. So what is this R plus n that I'm kind of annoyingly carrying around? So this R plus n, what they are, so note, n is the same number as faces.
Yes.
Right? What they correspond to is the sum of the lengths around each face. So they're the perimeters. Okay? Ultimately, they're going to correspond to the sort of proper size of the string. Sort of the integrated length of the string, or some asymptotic closed string state.
But what's the R plus n on the Riemann surface?
Well, that one's not here on the, so right now, that's going to be,
It's tensor on.
yeah, so right now what I'm drawing is just a part of this R plus n, sorry, of this MGN.
Yeah.
This R plus n doesn't show up in this picture. So later on what we're going to do, so if you just wanted to parameterize this, you would say fix the perimeters, but then individually vary the lengths.
Alternatively, you can also think about it as some border Riemann surface with 4 punctures.
That's another way of thinking
And
about
R+2
it. And then that would be the open string punctures. Exactly.
colors.
Okay. So let's just do a quick sanity check of the counting here. So we have 1, 2, 3, 4, 5, 6 edges. Okay. And we have 4 perimeters that are fixed. So there's 2 real numbers that are left over. And what do we have over here? We have 1 complex number as the moduli, which is a complex position on the sphere, on the Riemann sphere over here. Okay. So you can see how this matches. There's a nice sort of very quick sanity check you can do with graphs that tell you that the number of edges here is the same as the dimension of this moduli space. Got it? Okay. Good. So that's kind of just this equivalent. So what we're going to be thinking about is we're going to be thinking about these as Feynman diagrams, roughly.
And there's no additional identification on this product? This is just the direct tensor product?
Yeah, this one here, when we fix, so it can be a little complicated, but here it is just a product. But maybe one thing I'll say, if you want to,
The duality group acting on the MGN does not touch this
that R plus N, exactly. So if you want the automorphism, so the symmetry factors of these Feynman diagrams, okay, is going to be the same as the automorphism group of this surface. That's sort of how it maps 1 to 1. Okay, so great. So that's kind of on the math side. Let me try to say why physically you might think this is a useful thing. Okay, so first of all, hopefully I've convinced you that it might be useful for gauge string duality because we're going to be able to translate between diagrams that we're going to think of as the Feynman diagrams and 2D surfaces. So hopefully maybe that point is motivating enough. But I want to say something a little more about physically what's going on. Okay? So let's try drawing this graph over here, kind of superimposed on this 4-point function. So what I've done here is I'm just thinking of these punctures as sort of the asymptotic closed string states. That's what these asymptotic boundaries are over here. And so let's draw this Feynman diagram, so it'll look something like this. Maybe I'm being a little ambitious here. Okay, so this guy kind of wraps around. Okay, good. So you can see it's kind of like a harness that's holding this four punctured sphere together. So why is this useful physically? What's happening? Okay. What it's doing is that it's essentially writing your world sheet as a bunch of half cylinders, half infinite cylinders, glued to this Strabel graph. So we have 1 cylinder, 2 cylinder, 3 cylinder, 4 cylinders, and they're glued together along that graph. And that precise, there's a way that you can make that gluing very precise. We don't have to go too much into the details. The second thing I want to show is that it does even more for you, is that it actually decomposes the world sheet, so the closed string world sheet, into strips. And these strips, ultimately what we're going to think of these as physically, they're going to be thinking about them as the open string world sheets. Why do I say open string? It's because I'm imagining this gauge theory as arising as some open strings on some d-branes. Okay? So this gauge string duality is sort of a way of translating between open string quantities and closed string quantities. So one way of thinking about this gauge string duality is I want to take a bunch of open string world sheets and I want to glue them together to create a closed string world sheet. Okay, so let me show you how this works. So what does the Strabel graph do? The way that it reconstructs the world sheet is that essentially above every edge, so let's imagine we're looking at this edge here, okay, it's going to erect a semi-infinite strip, like this. Okay, so there's a semi-infinite strip right here. So it does it again for this edge, the one in the back, and then a one around. So this cylinder is built out of 4 strips that are glued together. Okay. So let me maybe just try to kind of draw that. So what this picture is kind of going on looks something like this. Okay. We've got a strip here in the back, another one like this. I'm really getting ambitious. Okay. So we've got this one in the front, this one on the side, this one in the back over here. So if you want, your closed string is built out of what you might call 4 string bits. Okay? So a natural picture for string bits. Now, you might have opinions about string bits. Maybe one thing I'll say is, if you're an integrability person, this is also very much the picture that people have of sort of when they look at spin systems describing some subsector of n equals 4, they think of each one of these little bits as a spin. Okay? And sort of how the spins interacts are essentially how these strips are getting glued together. Okay? I'll just say that. If those are helpful words, I'll leave it at that. Okay. Any questions about this part? So this is the geometry part, and then what we're going to do is we're going to try to work out an example, and then start from the Feynman diagrams of the Gaussian matrix integral, and sort of derive the string theory that comes out of it that way. Okay? Good. So, what are the string theories that are going to come out? It's probably worth telling you the answer before we try to derive them. So, in particular, we're going to be away from this double scaling limit. So when people study matrix models and strings, the duals to those matrix models are what are called the minimal strings. Okay? So minimal strings are, say, PQ minimal models, coupled to C equals 25 dB. Okay. So today we want to replace these strings by something new that are the duals of these type of matrix models that are studied.
25, right?
Oh, sorry. Thank you.
Depending on the PQ.
26 minus the central charge of the minimal model. Okay, so what are these string theories going to have? It turns out that because these string theories are so simple, they can sort of take on many faces. Okay, you can write the harmonic oscillator in a million different ways. Okay. So these are going to be 3 equivalent presentations of the same closed string worldsheet theory. And these equivalences go all the way back to the 90s. They were known back then. So what are they? So let's start with A. A is for a model. So this is a particular topological string. Okay. It turns out that in this, I had no idea what an A model was a couple years ago. Okay. What this is, it's a string, it's a path integral over maps that are just holomorphic maps to the target space. Okay. That's roughly how you should think of this A model. And which one is it? So it's basically a sort of topological version of a Wess-Amino-Witten model. Okay. With target SL2R mod U1. It's supersymmetric, and it's at this very special level, k equals to 1. Okay. This might be ringing some bells. This is the same type of worldsheet. It's a sort of topological version of the worldsheet theory that appeared as the dual to the free symmetric orbifold in ADS3 CFT2. Okay. So if you want, the story today is some sort of topological subsector of that ADS3 CFT2 story.
Isn't this is the center equal to 9, right?
Yes,
That's the conifold.
this is the confold as well.
This is what Sonia and Comrade studied.
Exactly. Yeah, great. Okay, good. So, yeah, okay, good. So, these topological strings, there's something called mirror symmetry that can relate them to another type of description. So B is for B model. You can see where I'm going. So C is for C equals to 1 string. I did this for you, Ahmed. Okay, so the second one is a B model topological string. And it's what's called a Landau-Ginzburg model. And if you want here, what I need to do is I need to specify a particular potential on the worldsheet. It's called the Landau-Ginzburg superpotential. And how do I find it? So the idea is that you give me some matrix model, and I'm going to spit out some potential. That's going to be the mapping between the two. And how do I find it? I look at what's called the spectral curve of the matrix model. So the spectral curve of the matrix model is a function of 2 variables, and I can write it as a curve. So it's the locus of some function being 0. I'm going to solve the spectral curve equation for one variable in terms of the other. And that is going to turn out to give me this So in particular, for the Gaussian, it turns out to be 1 over y plus y. Okay. So it's a very concrete thing, I can tell you. So finally, this equals 1 string. So what is this? This is going to be so it's also the self-dual radius. So let me tell you what that is. So this is a theory of a compact boson. Okay, one compact boson compactified at the self-dual radius, plus c equals to 25 Liouville. This time it's 25. So those are going to be the new string theories that we think about as dual to these matrix models. And in each one of them, we understand not just sort of a matching of the partition function, but a matching of observables. Okay. So in each one of them, if you tell me here, trace m to the k, I'm going to be able to map that to a particular vertex operator. These are the same vertex operators that were studied in the ADS3CFT2 correspondence. Over here, there's going to be a very, very similar story, but it turns out there's a very nice mathematical theory where I can write these directly as some sort of cohomology classes on MGM. We won't talk about that today. Finally, in the C equals 1 string, so this is a very, very simple string theory. There's not much that's going on. It's a 2-dimensional target. The only thing that can happen are vertex operators that are called tachyon operators. That's the only field in the target space. And it has some vertex operators. And the mapping is going to be that trace m to the k maps onto negative momentum tachyons. Okay, so this momentum is what's going to label this k over here on the trace.
So the last point is a little bit subtle, right? Because if you talk about the vanilla into 1 string, the x0 is in the time direction.
Yes.
Then you have the scattering states, but you don't care about the scattering states here.
Yeah, you're in Euclidean, so calling them scattering is a little. But there's a notion of correlation functions in this theory, and that's what they are. So,
It is what they call scattering numbers.
they get scattering numbers. Yeah, let's call them that. Okay, here. So it turns out that when we derive these dualities, there's sort of 3 different perspectives in which we derive the dualities, and I'll only tell you about one of them. But somehow each one favors a particular sort of worldsheet description. Okay. So the one that we'll talk about today is over here. This is when we really try to think about the Feynman diagrams as some sort of worldsheets. And that's going to naturally land us on this topological string here. The second one, it turns out, is the language of topological recursion. So if you've been working with matrix models, you might have come across this for a while. And here, there's an idea that we've dubbed open, closed, open triality. And I won't say, unfortunately, anything about that, but you should come ask me about it. Okay. Very good. So now what we're going to do is we're going to look at a particular Feynman diagram, map it onto a worldsheet, understand sort of the general way that you would do that, and kind of derive the string theory out of that. Okay. So any questions about this part? So far so good? Now's a good time for questions, yeah. Can people see what's over here? Yeah, this is readable.
Are you going to comment on if you consider other matrix models?
So
GOE and so on?
that will give, so that I don't know, but it should give rise to some sort of unorientable string theory. If you use symmetric matrices, you...
Have you go work down A models and B models for such companies?
No, not yet. This is still very new. So we still haven't really put out the paper on this A model and B model. So. Okay, good. So our goal now is to try to look at some simple correlation function of this, like this, okay, in the Gaussian matrix model, and try to reinterpret that as some vertex operators in the string theory. Okay. So let's try to do the simplest Feynman diagram in the simplest gauge theory. Okay. So we'll be looking at a contribution to something like trace m squared, okay, 4 times, I'll do this at genus 0. Okay. So what is a Feynman diagram going to look like? There are 4 vertices, 4 external vertices. Each vertex has just 2 legs coming out of it. That's this trace m squared. 4 vertices for this 4. Okay. This is clear? Yeah, great. Okay, so how are we going to map this onto some sort of world sheet theory? So the remaining second half of the talk, I want to do 2 things. I want to first interpret this here, if you want, as sort of seen from the world sheet. Okay. And then the second half will be understanding how do I think of that as seen from the target space. So I want to take all of these 2D surfaces and I want to embed them in the target space. And I want to tell you that the Feynman diagrams tells me both how to reconstruct the surface, but it also tells me how to embed it in some target space. So there'll be 2 parts here to this story. So we'll start with the world sheet first.
So just probably you said you just said the Feynman diagrams are in the Gaussian theory and the matrix is running constraint.
Yeah, they're Hermitian.
They're
Hermitian.
But which string theory are we looking at? Like you said, there are 3 different ones you can choose from.
So we're going to land on, if you want, we want to ask, why are we going to land on this SL2R mod U1 theory? Okay, why is that the string theory that had to pop out, right? That's what we want to understand, is the why, if you want. Right? So not just that it's dual, but sort of why is it dual. Okay. So hopefully I'll be able to answer that question too. Okay, just let me just add this together. So if you want, right, so this is kind of the simplest Feynman diagram we could be looking at. And first of all, what we need to do is we want to use this Strabel idea, okay? So remember here what we have is we have 4 vertices for 4 asymptotic strings, right? We want a 4-point function in the matrix model to go to a 4-point function in the string. So this, we want this to be somehow product I for 1 part. V2 to the 4. Some closed world sheet theory. So remember from the Strabel picture, there were as many faces as there were closed string insertions. So the first part of the story here is to actually look at the dual graph. Okay. So the dual graph will replace every vertex with a face. So what does the dual graph going to look like? It's going to look like this. So let me try to draw this Strabel graph directly on the world sheet with what's going on over here. We have one in the front, one in the back. Okay. And the thing I just drew is sort of doing this. Okay, that's that graph. So this guy is the Strabel graph. And this turns out to be graph dual to the Feynman diagram, the original Feynman diagram. It's going to be one important step in the construction. Okay. So remember, the other thing I need to do is to actually pinpoint a particular 2D surface. I need to assign some sort of lengths to these edges. So what is the prescription going to be? This is something that was proposed by Razamat almost 10 years ago. The idea is that you look at as many so you look at a particular edge, and you look at how many wick contractions there are between, that are sort of crossing the edge. Okay. So in this case, there's 1 wick contraction across each one. So I would label it 1, 1, 1, and 1. I would assign that length 1. If there was, for example, another wick contraction here, I would now assign this length 2. Okay. So the prescription is clear. Okay. So lengths is equal to number of wick contractions. But now we're faced with something kind of interesting. So the number of Wick contractions is always an integer. So what are we finding is that we're finding that all the world sheets that we're looking at are going to be parameterized by particular discrete points on the moduli space. Okay. So the coordinates on moduli space are now discrete. So the big punchline you should be taking here is that, in a sense, instead of trying to do a latticization of the world sheet, what we've done is that we've latticized directly the moduli space. So the picture is that you have continuum 2D surfaces, but you only have very, very special ones. It's going to turn out that these are actually very special surfaces called arithmetic Riemann surfaces. Okay, that's going to be a reason why mathematicians care about these particular points. Okay, good. So one thing you might have been asking over here is I told you earlier that the Strebel graphs are usually trivalent vertices, whereas you have quartic vertices here. Okay. And the way you should think about that is always about one of the lengths going to 0. Okay. So you should think of that, a quartic vertex, as sort of two trivalent vertices with a length 0 in the middle. So for example, this is going to be some codimension 2 subspace in the moduli space. Okay. Each length is a coordinate, so you kill off one of the coordinates, you kill off one of the dimensions. Now finally, I was telling you earlier that sort of physically what was useful is that we were trying to interpret this closed string world sheet as being built out of strips. Okay. And I wanted to identify those strips with the open strings of the world sheet, of the gauge theory. Okay. So where are those strips hiding here? Okay. What I want to argue is that you should really think of each edge of the Feynman diagram as an open string world sheet. Okay. So think about it. There's a I and j index. Okay. These are also indexing the d-branes of the original gauge theory. Okay. What you've done is you've taken some decoupling limit, or in this case, it's just a topological theory. The world sheet has no excitations. You've just kind of shrunk it to 0 size. Okay. So if you want, you should think of the double line notation of 't Hooft as really an open string world sheet. So where is this one hiding over there? Okay, so let me try to use some more colors. What's going on?
Edward, just to be sure. So previously we draw the triple graph as the harness. I mean, use the double line notation as well.
Yeah.
So
I should be drawing double lines as well. Yeah, I just got a little lazy there. Yeah. Thanks.
Just making sure.
No, definitely. Okay, so
but you don't have to if you just want to decompose them into cylinders.
That's right. So let's try to think about where this edge of the Feynman diagram is hiding on that closed string world sheet. So I'm going to drop these lines here. So they go from the edges to the vertices of the graph to the vertices of the full graph. So this diamond shape here. Okay. So where is that over here? Okay. These were the these 4 vertices mapped onto these 4 asymptotic closed string states. So where that strip is essentially like this. So maybe I'll try to draw it like this. I should know better that I can't do this. Okay, so what you've done, so this blue region here, which is one edge of the Feynman diagram, corresponds to sort of this quarter of this Riemann surface. Okay. And if you want, you've taken 4 of these guys and you've glued them together, again along this Strebel graph. Okay. So that's what's going on. So the idea is that the Feynman diagram edge is equal to 1 strip here. Okay. Which is you should think of as the open string world sheet. That's the picture that's coming along. Yeah.
Then it seems like open string has some finite length.
No, so this goes out to minus infinity. This goes out to plus infinity. So this actually.
I mean along the open string.
Ah, yes, exactly, great. So this has basically length 1 in this unit. So that's what I was just about to get to, thanks. So if you want, what is the length of this closed string over here? It's labeled by this 2 over here, okay, this trace m squared. If you want, you have an m here and an m here, m here and an m here. And what you've done is you've created a closed string out of 2 string bits that you've glued together like this. Okay? So say trace m to the k will create a string of size k. Okay, so the lengths of the strings are also integers here. Okay, so maybe that's another punchline. Trace m to the k sort of creates an asymptotic closed string state with length k. And there's a particular metric called the Strabel metric that I haven't mentioned, but it's relative to that metric that I'm computing this length.
So you're just taking a particular frame?
Yeah, so if you want, kind of what's underlying this is a very judicious choice of gauge on the worldsheet that makes the duality with the Feynman diagrams very obvious. That's really what's going on. So it's something called Strabel gauge. This whole Strabel business comes from choosing a particular gauge on the worldsheet that makes this clear.
And you not gauge these lines arbitrarily straight.
Exactly. This is a gauge that's often used in string field theory. So I should say that this is a classic tool in string field theory. What I'm saying about Strabel is nothing new. I'm just trying to use it for the purpose of gauge string duality here. But this is a very old tool. Okay, so let's now try to take this little example and in kind of one slide, think more generally now about that correlator. Okay. So what we want to understand is what is kind of the string interpretation of a correlator like this. So what would you do, right? You'd sit down, or you'd have your grad student sit down, and he does all the weight contractions. Okay. And what that means is that he would be summing over Feynman diagrams. It's mostly postdocs in here by now, so we've probably had some undergrad. Yeah. You might be doing the weight contractions, I'm sorry. Okay.
You will actually be doing topological equations.
So you'll be summing over these Feynman diagrams. They'll be of genus G. Okay, that's what's this G over here. Okay, that's a term in the 1 over n expansion. And there will be n vertices because there are n traces inserted in this correlator. And each of these vertices have valency ki. Okay, that's the first picture we drew over here. Now I just want to do the same thing here, but just thought of as a sum over the dual graphs. Okay. So what are the dual graphs now? Those are now Strabel graphs. Again, they're going to be genus G. Genus doesn't change. The vertices in the dual graph go over to faces. So we now have n faces. The valency of the vertex becomes the perimeter of the face. So those are ki perimeters. And they all have integer lengths. And again, integer because it's the number of weight contractions in the original Feynman diagram. So let's think about what this is. So let me now draw MGN. This is MGN. So each graph, okay, each Strabel graph is 1 point on the moduli space by that exact equivalence I told you. Okay. So what am I doing is that I'm basically summing over all of these points. And in the conventions I've taken, the propagator is just 1, so I'm just basically counting these points. Okay. So each point is one of the Feynman diagrams.
Up to the signature factor.
Up to so it turns out that that's why we map to a point on MGN directly. Yeah. So it turns out that this is actually a problem studied by mathematicians, maybe under the unimaginative name of lattice point counts on moduli space. MGN. And if you pick up your favorite math paper on the subject, they're often tables. So these numbers are labeled by G and N, the same G and N over there. And these integers here, K1 through Kn, those are the same as the k1 through kn. So again, just if this maybe isn't totally clear, let me just try to emphasize this. These ki's are coordinates on this r plus n factor, right? Those are the n numbers that I'm specifying in r plus n. So once those are fixed, everything else is just happening in MGN. And if you want, if everything I'm telling you is true, you should be able to go to these appendices and check whether they agree. So you go and you compute these things in the Gaussian matrix model, and then you check, and indeed they match. Okay, so this is a very reassuring thing. So one thing you might be worrying about is what type of string theory could possibly do something like this? This seems like a totally crazy thing for a string theory to do. And I'm going to tell you shortly that it turns out that the string theory, what it wants to do is it wants to cover the target space. The target space is going to be a sphere. And it turns out you can't take every 2D Riemann surface and wrap the sphere in that particular way. Okay, it's going to turn out that only very, very specific world sheets can wrap a sphere in that particular way. Which ones are they? They're going to be exactly these points. It's a beautiful theorem by a mathematician called Belly.
Target space is how many dimensional?
The target space here is just going to be two-dimensional, just going to be a sphere. I'll talk about that
Sphere.
hopefully. Yeah, 15 minutes, I think that should be doable.
From the resolved contours.
Well, in this case, for the A model, it's just going to, yeah, I think you can think of it that way.
Because eventually, I mean, it's the conical, which is n-dimensional. Sorry,
This twisted SL2R mod U1, I think really as a target only has that P1 in it.
And from the conical perspective, that P1 presumably comes from the
Yes, it is that SC2. That's right.
So it's the kind of the normalizable modes are concentrated.
Exactly. It's like you've gotten rid of all these normal bundles on that. Okay, great. So I want to make one last statement here about trying to connect to some things that you might already be familiar with from your usual experience with matrix models, if you have any. Where how do we connect to the double scaling limit? To the double scaling limit. Okay. So which is where usually people think about matrix models. So I'm not actually going to take a double scaling limit. That's not what I want to do. But I want to engineer some limit of these correlators that's going to sort of reproduce the same effects as taking this double scaling limit. So it's going to be akin to something like the BMN limit in the CFT. So I'll kind of say it's BMN-like. Okay. If you write things in other colors, it's never wrong. So that's the idea. Okay. So what am I going to do is I'm going to look at the limit of these ki's to be very, very large. So I'm looking at very, very large operators in this correlation function. Okay. So I'll first tell you the math statement, and then I'll tell you physically what's going on and what this has to do with the double scaling limit. Okay. So this guy we've already established are these lattice point counts. And it turns out this limit is very well studied in the math literature. What these end up doing is they go over to some sort of continuous volumes of the moduli space, labeled essentially again by these k1s. Okay. So what's the picture here? Okay. Is that as the k's become very large, you have many, many more Wick contractions that you can do. Okay. So for any given k, I had some finite number of points. Those are the things that this Gaussian matrix correlator is computing. Now, take the vertices and now put a bunch of legs. That's this very large ki limit. There's many, many Wick contractions I can do, and each given Wick contraction is one world sheet. So in this large ki limit, what am I doing? I'm adding more and more points. And I keep doing that, and it turns out, so that's the hard work of the mathematician, that converges to a continuous integral over MGN. So that BMN limit does something going from these points to this continuous integral over moduli space. Okay. So, well, this is not a typo. This K is actually for Konzevich, but that's what these particular volumes are. There's a particular volume form on there. Okay. So let me try to tell you physically what's going on over here. Remember we said that basically each closed, these diagrams are very similar. Okay, the thing I'm drawing right now is a closed string. Okay, it's not this moduli space. And we were saying that each of these strings is sort of built out of some discrete number of kind of string bits. They're kind of like rigid rods, if you want. So when there's a finite number of rods, if you want, the string can only kind of do discretely many configurations. Those discrete configurations are these points here. When I take ki to be very large, that's the number, right? There are ki string bits here. When this number becomes very large, the string can sort of essentially do anything at once. Okay. And that's the same sense that I can cover this moduli space densely. Okay. So what the hell does this have to do with the double scaling limit? Okay. So actually, I think it'll be easiest if I just added some factors of 2. There we go here. Okay. And now let's think about this trace. So in the Gaussian matrix model, we can look at the eigenvalues of each of these matrices. So everyone here is familiar with the Wigner semicircle, right? So I'm looking at the density of eigenvalues given a particular value of the eigenvalue. So this is just some histogram of all the eigenvalues of some big n by n Gaussian matrix. Okay. So what does this trace of m to the 2k look like? So this is just a sum of the eigenvalues to the 2k. Now what happens when k becomes very, very large? This sum is just going to be dominated by the largest eigenvalues. Right? So what's going on is that when we're taking this large ki limit, what we're doing is that we're basically focusing in on the edges of the distribution. These are the biggest eigenvalues that are appearing. Now for matrix model practitioners, you might recognize this as what you do in the double scaling limit. You take this distribution and then you just focus on the edge of the distribution. Same thing happens, say, in JT gravity, where this would be like the spectral density. Okay. Good. So any questions about this? So in the remaining 10 minutes, I'll try to give you a bit of a picture about the target space. Okay, so this was the worldsheet picture. And now what we want to do is we want to take all of these 2D surfaces and we want to put them in, say, the ADS if you want.
If you do this double scale limit, in this case, you get the Konzevich matrix model that directly calculates those values.
Not directly from this model, but that's where this...
This is from the other open,
closed, open,
yeah.
exactly. So that would give you exactly this Konzevich model. And one thing we kind of derived is a Konzevich model for these discrete volumes. Yeah, exactly.
Okay, so the quantum version.
Like a quantum fusion. It's like, yeah, exactly. Like some Q-deformed Konzevich model.
Exactly.
And you might be thinking, what does this have to do really with string? I mean, say, Konzevich model was derived by Restelli and Gaiotto
Yes.
as literally the open string field theory on FCZT brains. So I mean, these matrix models, you might not believe me, but they really are describing some open strings. I mean, I didn't talk about that at all today, but they're more than just little toy models. Okay, good. So remaining time. Great. So in the last 10 minutes, yeah, 3 minutes over is okay. Yeah, you're the boss.
Yeah,
He's the boss. Okay. This is how you know who the real boss is. All the department dynamics come out in this moment. Okay. So the second half, if you want, is the story as kind of seen from the target space. And so what is going to be the idea? So what I want to do is I want to start with my Feynman diagrams, and I want to write these as some sort of maps. So this A model string theory is a sum over holomorphic maps. Okay? So I want to write the sum over Feynman diagrams as some sort of sum over holomorphic maps. Okay, so that seems crazy. The intermediate step that we're going to do in order to make this happen is to actually do the following. We're going to write the sum over Feynman diagrams as a sum over certain permutations over permutation triples. So And each one of these permutations, okay, so each one of these permutations, I'm going to be thinking about a particular branching structure of a map. So these are going to be holomorphic maps that are covering maps of a target space sphere, a CP1. Okay. And these maps are going to be branched over the target space, and they're going to be branched over exactly 3 points. What this sum over permutation triples is going to do is I'm going to basically assign each one of these 3 permutations to the way that the worldsheet branches over that target space, over those 3 points. Okay? So we can say take those 3 points on the target space sphere to be 0, 1, and infinity. This seems very abstract, but I'm going to do a very concrete example. Okay? So this will be sort of the branching above 0, branching above 1, branching above, say, infinity. What's going to be very nice is that each of these permutations have a very nice graphical description at the level of the Feynman diagrams. They're going to be associated respectively to vertices, edges, and faces of the Feynman diagrams. Okay? So this seems super abstract, so let's just try to do an example here. So here's our favorite Feynman diagram. Okay. And the way that I'm going to associate particular permutations is going to be as follows. So this is probably going to look like black magic. That's okay. From a math perspective, these Feynman diagrams are something you might have seen under the word of child's drawings. So this is a famous thing by Grothendieck, also called dessin d'enfant.
Exactly.
It turns out, yeah, Grothendieck was super impressed that you could write these holomorphic covering maps of a sphere in terms of some diagrams. Turns out that these diagrams are just the gauge theory Feynman diagrams. So Grothendieck would be hopefully happy about this. So how does it work? Okay, so let's take this Feynman diagram, and I'm going to break each edge into half edges. Okay? So there are 8 half edges, and the 8 is going to be the degree of the cover. So I've taken some artistic liberties to draw my target space sphere as a line. Okay. This is the North Pole, the South Pole, and say 1 on the target space line. And we have a worldsheet that's wrapping this target space sphere 8 times. Okay, so it's going to be a degree 8 cover. Okay. So how do I specify this branching? Okay. So you need to take some prescription, it doesn't really matter. So we'll take some orientation to the half edges. Say it always goes from circles to squares, and I draw some number on the right. Okay, so here I draw a 1, here I draw a 2. I go around my diagram like this. Okay. And so now I can write down permutations by looking at the vertices or the edges or the faces. So let's start with this vertex. This will have a 1-8 permutation. So that means that I'm going to take the first cover, and it's going to sort of get swapped with the 8th cover. Okay, you're a little ant on the world sheet, you walk here, and then all of a sudden you end up on this 8th covering. So okay, you could do that same here, 2, 3, 4, 5, 6, 7. That's that first permutation. Okay. Now we can do the same thing for the edges. Now note that the edges are always just going to be a bunch of 2 cycles. That just corresponds to the width contractions. Okay, when I have m, and I'm width contracting them. Okay, so we have, say, 1, 2, 3, 4, 5, 6, 7, 8. So it's over here. And then finally, the last one is going to be the faces. So this turns out to be a sort of slightly more interesting permutation. But here we could say 1, 7, 5, 3. And then here we have to go the other way around. That's the orientation of the faces. 2, 4, 6, 8. Okay. So let's follow this. So say for the edges now, above 0. I start with the vertices. So 1 goes to 8, that's this line over here. Then what happens to over 1? So 8 gets permuted with 2. Okay, so 8 goes up to 2. And now where does 2 go? 2 gets permuted with 1. Okay. So it turns out that all of these permutations, they have to multiply to the identity. This is saying that you have no non-contractible circles on the sphere. So it turns out 0, 1, infinity is sort of the identity.
So I missed why you
Yeah.
went in that order. 0, I mean.
It's
vertices-
about this ordering.
No, I mean, you start with the vertex, you start with the vertices, then you went to faces, and then you went to edges. And when you applied the rule of what goes to what, the permutation. Went
Yes.
from 8 to 1, then you said 8 to 2.
Yes, so right now this is a prescription, and hopefully I'll be able to tell you a little where that comes from.
Okay,
So right now it's just, I'm just giving you some dictionary that for every Feynman diagram, you can write it as some map.
okay.
Good. So again, the thing I want to call, so these are very special objects called belly maps. And so these are maps that are covering the sphere branched over exactly 3 points. And again, you can't take any Riemann surface and do that. Which are the ones that you can do that? Those are exactly these points that are labeled by integer stribelgraphs. It's a beautiful theorem, I know. Okay. So what does this have to do with this SL2R mod U1? Okay, that's ultimately what we wanted to get at. So what was shown in the ADS3 CFT2 correspondence is that at this very special level 1, the path integral localizes to covering maps of a sphere branched over points. And if you wanted the sort of work that we've had to add is that to show that they're branched over exactly 3 points. Okay? So localization of this path integral, so to covering maps of the sphere. P1. Okay, so this was shown already by, so this was Eberhardt, Gabriel, Gopakumar, Bob Knight, and Pranavesh in the ADS3 CFT2 context. Okay. So if you want, what is the crazy string theory that gives you exactly these worldsheets? It's this worldsheet theory. Okay. So that's how we find this worldsheet theory as the dual to the Gaussian matrix model. Okay. So if I can say one last thing, I'll just maybe try to tie these 2 stories. So I gave you 2 stories. One was how to reconstruct the worldsheet, and how to reconstruct the maps into the target space. And those 2 stories might seem very distinct. Okay?
So this special about the 3 coming from this, from the perspective of this concept.
Yeah.
String theory defined by the concept.
So
Like
two,
if you were to consider more general homomorphic maps with more branched points.
you would
what
have
would you
more
do?
and more multi-matrix models. So what I didn't really explain well today is there's secretly a 2-matrix model hiding behind this, and that turns to, that's essentially what these half edges are. So these are vertices of another matrix. I swept that under the rug today. So a 2-matrix model basically has these, the traces of one matrix sort of get mapped to the north pole, traces of the other matrix get mapped to the south pole. This third point comes from something quite subtle. It's about degenerate representations of the identity in this cosine space. So it's a non-trivial thing. Okay. So let me just give you one last piece of information as to how those 2 stories tie together, okay, which I personally think is very satisfying. So let's go back to this Feynman diagram, right, and think about a single strip. This was the open string strip, right? So that was this diamond piece here that again I've tried to draw here. And so the half edge is kind of, if you want, halfway through this width contraction between n and n. Okay. So the idea is that, so each one of these is just a semi-infinite strip, and each string bit has sort of length 1. Okay, so this is the complex z-plane, it's just a strip. So these 2 points are just 0 and 1. Okay, this guy is at half. Okay, this vertex is at plus I infinity. This vertex is at minus I infinity. I'm just writing down this strip. The point is that we can write down an explicit map of each strip into the target space. Okay, so this is how every little patch of the string gets mapped into the target space. Okay, so this is the strip, and it's going to get mapped into this target space P1. The map is this, so this is going from Z coordinates into coordinates on the Riemann sphere. This is zeta. It's very, very explicit, cosine squared. Okay? And you can check that it takes plus I infinity and minus I infinity up to here. It takes 0 and 1 down to here, and it takes this half to 1. Okay? So what's the final punchline? Is that if you take every strip and map it into the target space like that, and then you glue each strip according to that Strabel construction, that gives you exactly this branched cover. Each strip wraps the world, each strip ends up wrapping the target space twice. And then gluing the strips is this complicated 8-degree cover. Okay. So that's how those two stories fall together nicely. Okay, so I'll stop here, and yeah, answer any questions. Thanks.
Questions?
So these points in the moduli space you pick out, they have very interesting number theoretic properties.
They do.
I know I have to ask, you know that. Do you see them in the gauge theory at all?
Do I see them in the gauge theory? Well, they're the Feynman diagrams of the gauge theory.
I know, but the fact that there are secretly modular forms and all that interesting stuff, does that have
I don't know.
an imprint on the gauge theory?
Ultimately, where this integer structure came was from our choice of this length assignment. So, when I gave you some Feynman diagram, I sort of had to come up with a way of assigning a length to each edge. And this is one particular prescription. It turns out it's kind of the right one, if you want. That's kind of what you see from the consistency of this story. But that's where kind of all the interesting part comes from, is the fact that those are integers. I don't know how to see that directly in some... Well, I guess it's the fact that every correlator of the Gaussian matrix model is basically some integer, right? You're just counting some number of weight contractions. So, yeah, it's about that.
Yeah. Normally when you're counting branch coverings, it's like ELSV type formulas that write it as an integral over the moduli space. So in your picture here, should I think of this as like some sort of where the ELSV, like the integral localizes over these points, and you have some sort of analogy with the...
Great question, yeah. So it turns out that if you want, I was making a big deal about the integrand on moduli space being basically a sum of delta functions here.
Yeah.
But the integrand on moduli space is not a physical quantity. You can always shift it by some QBRST or something. Okay. So it turns out that in the B model, this is not at all the picture. What you have instead is a nice continuous integrand all over moduli space. The final integral, which is the physical observable, agrees. What that integrand is essentially a sort of generalization of the ELSV formula. So instead of Hodge classes, you can write it in terms of the psi and kappa classes. So there's a very sort of reminiscent formula. So one thing we also did is basically compute all of these numbers, so reproduce the Gaussian matrix model correlators from integrals of those characteristic classes of GN. And that's like the ELSV formula. Does that answer your question?
Yeah.
Can you also comment on the C-type figure?
Yeah, so for the C equals 1 string, right? I mean, same thing here. It's very hard to imagine the C equals 1 string in this language. I don't think anyone envisioned any sort of localization or things like that.
There's a relation between the A and C related by a topological twist.
Yeah, exactly. Well, so they're both equivalent, right?
Yeah.
Right. I mean,
You can start from the physical string where the dimension 9 internal CFT is literally the 8/2 coset,
yes.
and then you can do the topological twist, and then you go to this bosonic.
That's right. That's right. Yeah, I mean, roughly the idea is that you do a Wakimoto representation of that current algebra.
Yes.
You sort of massage it until you write all the currents in terms of 2 fields.
Mhm.
One ends up being the Liouville field, and one ends up being this boson.
Yes.
So that's kind of the massaging that you do in order to see how C equals 1 appears. But I don't know what that means at the level of...
Yeah, would you say
they're
there's a
equivalent.
localization that happens again at the level of the integration of the modular space, and then you just end up as the sum of integral points, just like in a model case?
No, I don't think localization happens there either. In
You
C plus one, no. So again, I think it's so in that derivation of Vafa and Muki,
Yeah,
it's important to add some BRST total derivatives,
see.
and that will actually spoil this picture. But I mean, one thing that we did was, just compute some high 1/n suppressed terms in these correlators, and we looked at old C equals 1 papers by Klebanov from the 90s, where they had up to genus 3, and those just match. I mean, it's very nice to see. Like, yeah, it's passed many checks so far, so that's been very nice for us. So.
Have you thought about turning on the potential?
Right, so I think one thing that happens in this talk is that people get the impression this is just for the free Gaussian matrix model. The point is that once you understand the dictionary between, say, trace m to the k and some vertex operator, you can now take the action of the free theory and you add this vertex operator to it, and it'll be true to all orders in perturbation theory. And that perturbation theory ends up being the 't Hooft perturbation theory. So, put like a lambda trace m to the 4, then a lambda v4, and now you're just doing perturbation theory in 't Hooft, which is convergent. So it has some finite radius of convergence. I don't know what to say about the very strong coupling. But at least we know how to go to some finite range around the free point. And this story of covering maps seems to be quite general. So somehow Rajesh's big dream is that all duals to free gauge theories have some sort of covering map story like that. So that turned out to be true in the symmetric orbital fold case. And they have some proposal for the worldsheet dual of free n equals 4 super Young nodes. That turns out to have a similar localization to covering maps, but in twister space. Very long along the lines of Witten's twister string theory.
But let me make sure, so in the free to 4 super Young nodes, the matrix model is essentially...
It's not a matrix model there. So
Oh, okay, so you consider, literally okay.
Yeah.
Not the localized version.
yeah, no. They're really taking full
Matrix
theory.
theory.
Yeah.
So in this case, if you really think about the condensate formed by the gold strings, how should one think about how the target space is deformed?
That's a great question. So I like to somehow think of it as somehow, squashing the sphere in some way, but I don't have a good answer to that.
But how would this squashing parameter enter in the A model result?
Well, it would enter in deforming the action of the SL2R1U1 theory.
Good.
So you would add
Good.
some perturbative term, and you would
Kind
deform
of,
the action.
can I think about it as coming from the killer class associated with the...
That's what I'd like to be true, but I don't know how to show something like that yet.
All right, if there are no further questions, let's thank
Okay,
everyone.
thanks again, guys.
When is the work coming out?
Yeah, so one of them about this open-closed open is out, but yeah, hopefully this A model should come out not too long.